paradoxes are good. That's a paradox, of course, because paradoxes force you to think. When David and I began the work that led to this Nobel Prize in 1972, we were driven by paradoxes. In resolving these paradoxes, we were led to a new principle, asymptotic freedom. This principle led to a new concept of what a fundamental particle is, a new understanding of how matter gets its mass, a new and much clearer picture of the early universe, and new ideas about the unity of nature's forces. Today, I'd like to share with you the story of these ideas. The first paradox was phenomenological. Quarks are born free, but everywhere they are in chains. In the early 1960s, Murray Gell-Mann and George Zweig made a great advance in the theory of the strong interaction by proposing the existence of quarks. For many years, physicists had gathered data on the nuclear interaction, basically by bashing protons and neutrons together and studying what happened, what came out. What emerged was a plethora of new particles. Although these particles, generically called hadrons, were unstable, they had interactions that resemble those of protons and neutrons quite closely, and so clearly it was one subject. This new subject grew. It was no longer the theory of atomic nuclei, or the study of atomic nuclei. We were clearly dealing with a new force of nature, the most powerful, which became called the strong interaction, that all these hadrons must feel. As the data accumulated, it was compiled in a big set of tables. You saw a small sample of it. Superficially, it appeared to be quite an amorphous mess. But if, with Gell-Mann and Zweig, you imagine that all these new particles, these hadrons, were not fundamental, but rather assembled from a few more basic types, the quarks, then patterns, beautiful patterns like this, clicked into place. The rules for working with quarks, however, and assembling them into hadrons were quite strange. Quarks were supposed to hardly notice one another when they were close together, but when you tried to pull one away from its partners, you could not. You could not isolate a single quark. People looked very hard in experiments and at very high energies, bashing things apart as hard as they possibly could for individual quarks, but without success. Only bound states of a quark and an antiquark, or of three quarks, are observed. This regularity was elevated into a principle, the principle of confinement. But giving it a dignified name didn't make it less paradoxical. It was an unprecedented phenomenon in physics. The paradox only got sharpened when Friedman, Kendall, and Taylor, in their pioneering experiments at SLAC, used energetic photons to poke inside protons and look in a very literal way at the inside. They found that there are indeed entities that look like quarks inside protons, and they found that when quarks are hit hard, they move as if they are free particles. This was a big surprise to most physicists, because before the experiment, most physicists had expected that whatever was causing the strong interaction of quarks that kept them confined would also cause quarks to radiate and slow down when they got rapidly accelerated. The second paradox was more conceptual. Quantum mechanics and special relativity are two great theories of 20th century physics, and each one is extremely successful. However, the concepts they employ are quite distinct, and in fact, they're not easy to reconcile. Whereas special relativity puts space and time on the same footing and postulates symmetry transformations that transform space into time, quantum mechanics treats space and time very differently. This leads to a creative tension. Several Nobel Prizes, in fact, have revolved around the question of reconciling special relativity and quantum mechanics, and ours is another. Dirac discovered the equations for particles and was led to the discovery of antiparticles. Nowadays, we can understand why these mathematical manipulations, which at first were just that, mathematical manipulations, had a certain inevitability. If you have a very rapidly moving particle moving at close to the speed of light, and yet its position is uncertain, you might have measured wrong, and maybe it's moving a little faster because it's gone a little further. Then it would be moving faster than the speed of light, but special relativity doesn't allow that. The way to reconcile that is to have additional complications, and that leads to antiparticles. Another thing that quantum mechanics allows is that there are fluctuations that have additional energy for short amounts of time. It allows fluctuations of increasing in the energy in a state for short amounts of time. This leads to the concept called virtual particles, that empty space that we see as empty is in fact not empty, but contains these fluctuations. So nature can temporarily borrow a little bit of energy to make particles and then has to give it back, so they live only for a short time. We call them virtual. These virtual particles, which turn empty space into a dynamical medium, cause terrible mathematical difficulties. Feynman and Schwinger and Tamanaga, in the context of quantum electrodynamics, solved these mathematical difficulties, and by showing that they were necessary, in fact, to explain experimental results, convinced physicists of the reality of virtual particles. And in Hooft and Veltman, in a much more complicated context of electroweak gauge theory, vastly increased the scope of the concept of virtual particles and showed its mathematical consistency. All these brilliant works, however, which deservedly were rewarded with Nobel Prizes, did not solve all the problems. In fact, the most profound problem, perhaps, was identified by Landau. He argued that virtual particles would always tend, since they're in empty space, constantly coming to be and passing away, would always accumulate around real particles as long as that real particle had any uncanceled influence. The virtual particles would feel that influence and until the influence was canceled, keep fluctuating and be disturbed by the introduced particle. And in fact, it's worse because the virtual particles, being particles themselves, in turn induce disturbances. And so the only stable situation is when the influence is completely canceled, and this is called screening. Landau's intuition was that screening would completely would go on and be an unstable process until the original charge were completely canceled. So it had no remaining influence. That was the only possibility. And he backed up this intuition, he and his school, with calculations in many different kinds of quantum field theories. And they found that that's indeed what happened in all the cases they calculated. And so they postulated, or they concluded, that quantum field theory was inconsistent with describing interactions, ultimately. And they viewed this as a very encouraging result because in practice, quantum field theory had proved useless for describing the strong interaction. So we had two severe paradoxes. One phenomenological, that quarks sometimes appeared to behave freely and at other times clearly far from free, and the conceptual paradox, trying to reconcile basic principles of quantum mechanics with relativity. These paradoxes were resolved by our discovery of asymptotic freedom. What we found is that some very special quantum field theories have anti-screening, which then we called asymptotic freedom, a coinage coming from Sidney Coleman, actually. The theories involved are called non-abelian gauge theories, or Yang-Mills theories, after their discoverer. They form a vast generalization of electrodynamics because they postulate the existence of several kinds of charge with symmetry among the several kinds. So instead of one entity, electric charge, that you have in electrodynamics, we have several entities which we call different colors. Also, together with that, instead of just one photon that we have in electrodynamics, we have a family of gluons that respond to and change the different color charges one into the other. In QCD, there are 8 such gluons. Asymptotic freedom means that a small central charge, instead of being canceled, starts to build up an effect that becomes more and more powerful at large distances. It explains not only how interactions can exist consistently, but how the same basic interaction, can appear either powerful or feeble, depending on the circumstances. You get feeble forces if you penetrate well within the cloud of virtual particles. The cloud of virtual particles grows from a very weak seed to become a sort of thundercloud of bigger and bigger effects. You get feeble forces if you penetrate well within the cloud to see the small seed, but powerful forces if you're far away and feel the effect of the whole cloud. And so in space, you see that the interaction appears feeble at small separations, but powerful at large separations. This is just the behavior we wanted to understand what was postulated in the quark model. Viewing the same thing in terms of energy, we find that the interaction, that when you jerk the seed of the cloud very violently so that it leaves its accumulated cloud behind, it is a very weak influence, and so doesn't induce violent radiation, and also is not radiating rapidly or slowing down, consistent with the behavior revealed experimentally by Friedman, Kendall, and Taylor. The clouds, which eventually will accumulate around these seeds, around these quarks or gluons, build up only slowly and gradually. So in that way, we were able to, in a stroke which I hope you can understand conceptually, resolve the profound paradoxes that seem to be presenting themselves both phenomenologically and conceptually. This picture of the dynamics of charge and its development has revolutionized several areas of fundamental understanding in physics, leading to new paradigms. The first paradigm is the hard reality of quarks and gluons. Asymptotic freedom has been a great boon for experimental physics because it leads directly to the beautiful phenomenon of jets. Remember, I told you that you couldn't liberate individual quarks and gluons from outside of the hadrons. And yet here, I can show you, in real experimental data, a picture that contains a quark, an antiquark, and a gluon. You see them not as individual particles, that's what I told you was impossible, and I'll stick by it. But rather what you see is the flows of energy that those fundamental particles induce. Initially, you have rapidly moving quark and antiquark and gluon, as they don't radiate powerfully in a way that deflects them very much, but they do radiate softly, building up their clouds in a way that doesn't deflect them very much, but does change them from single particles into whole sprays of particles moving in that same original direction. So you get to see the initial quarks and gluons through their imprinting the flow of energy and momentum on these jets. So quarks and gluons, which were these embarrassments, especially in the modeling of hadrons, these things you couldn't isolate, now have become the staple of high-energy physics, and experimentalists analyze their results literally in terms of quarks and gluons, and without embarrassment, even though they've never found either one of them individually. By analyzing the probability for different angular distributions between these jets, how it changes with energy, the possibility of sometimes having 4 jets or 2 versus 3, things like that, you can relate the fundamental principles of the seed charges and how they interact with each other, where it's simple, to experimental realities. And that's been a slow but very gratifying process involving thousands of physicists all over the world doing very different kinds of experiments, and also theorists working very hard to interpret these experiments. And the result is what you see here, that the theoretical prediction of how it gets more and more difficult to radiate as the amount of deflection caused by the radiation gets larger, what we call the energy or momentum transfer gets larger, that should get smaller as the energy gets larger, is verified. The theoretical curve beautifully agrees with the experimental curve, and, well, here we are. The second paradigm is a new understanding of the origin of mass, that mass comes from energy. This is an instantiation of Einstein's second law, m equals E over c squared. In the Army training manual for radio engineers, you will find that there are 3 Ohm's laws. Ohm's first law is V equals IR. Ohm's second law is I equals V divided by R. And I'll let you conjecture about Ohm's third law. So together with Einstein's famous law, E equals mc squared, there's Einstein's second law, m equals E divided by c squared. Now, that may seem frivolous or silly, but it's actually quite profound, because the equations suggest quite different things. E equals mc squared suggests that you should think about getting energy out of mass. But in modern physics, energy is a much more primitive concept, a much more central concept than mass. And the right way to write the equation is really m equals E divided by c squared. This suggests the possibility of deriving mass from energy, which is the more primitive and central concept. Interestingly enough, this is the way Einstein originally wrote the equation. In his first paper, you will not find E equals mc squared, but this form, m equals E divided by c squared. And the title of the paper is, Does the inertia of a body depend on its energy content? And the answer we're providing is a resounding yes. In fact, its inertia is entirely determined by its energy content in QCD, to a very good approximation. So the theory has to produce not only these jet phenomena, not only the simple parts that involve the seed charges and their rapid motion, but also all the phenomena of the strong interactions, including this messy table of hadronic masses that we started with, the original problem. To do the necessary calculations has proved very challenging, and the only technique that's really succeeded is to directly discretize the equations, feed them into a computer, and let the computer work very hard. In fact, these kinds of calculations have pushed the frontiers of massively parallel computer processing, computer calculating. The result is very gratifying, though, because you find that the basic theory, with no room for maneuver, this is a very, very tight theory governed by enormous symmetry, just as electrodynamics, its cousin, is. This very, very tight theory with no room for maneuver, having to reproduce that table of masses or just be wrong, is doing a remarkably good job of reproducing the masses. The observed masses are shown by the level green lines here of various hadrons, and the calculated masses are shown by the data points. These are sort of numerical experiments. And this is not quite state of the art. There are some sources of error that are known, but you can see that we're doing very, very well, especially when you reflect that what goes into these calculations that are calculating the masses of hadrons are essentially massless ingredients. You start with strictly massless gluons and quarks, which have very, very small mass compared to the total masses of the hadrons they constitute, and almost all the mass is coming Einstein's way from m equals E divided by c squared. That may seem rather abstract, but the calculations can also be massaged to make beautiful images if you just present them in an eye-friendly way, and it's also informative to do that. What you see here is one of the simplest hadrons, the so-called pion, being created over here. You just stick in, this is a numerical experiment, so you have a lot of flexibility. You stick in something that will create a pion here, take it out over there, and look at the pion moving through space-time. You can study the fields. Now, the fields are actually fluctuating a lot, but they average over them to get a sort of effective wave function. So this is the pion moving through time in the simulation. This is what for the physicists in the audience, you'd call the wave function of the pion. You take a slice, and this is what pions are made out of. Protons would make a very similar picture. So this is what you and I are made out of, these clouds of energy and excitations of the fields. If we don't average over the fluctuations, then we can see in a real way the dynamical behavior of the fields in space and time. For the experts, this is real data, real numerical data on what happens in empty space in QCD. So this is what's happening all the time within us. We have these little lava lamps. These are fluctuations in the quarks and gluons. This is actually, for the experts, what's actually shown here is the topological charge density of the gluon fields with some smoothing. But in any case, the reality of the quantum fields here and their fluctuations means that empty space is a dynamical medium. You can study it, you can simulate it, you can picture it, and the various particles, the protons, neutrons, the other hadrons, are all understood as the tones that this medium emits when you pluck it in different ways. When you hit the gong in different ways, you can get it to emit different tones. Those tones are the masses of the different particles. The third paradigm that comes out of asymptotic freedom, pretty directly, is that the early universe is simple. In 1972, the early universe seemed hopelessly opaque. At high temperatures, one would produce lots of protons and antiprotons and other hadrons and antihadrons, lambdas and antilambdas, pions, rhos. So many of those things that at high temperature, in the early moments of the Big Bang, they'd start to overlap one another. They interact strongly. And so it appeared to be a hopeless mess. But asymptotic freedom, instead, is friendly to high temperatures. It says that at high temperatures, if you turn away from the description in terms of hadrons toward the more fundamental description in terms of quarks and gluons, things get simpler instead of more complicated. In fact, at the highest energies, quarks, antiquarks, and gluons move freely. We can understand that. So it's been possible, using that insight, to talk sensibly and with a straight face about the physics of the early universe, and that's been a very fruitful endeavor. Now, we can even, to a certain limited extent, reproduce the Big Bang in the laboratory by colliding large nuclei together at high energy, producing a very hot fireball. We reproduce the conditions in a small amount of space and for a small amount of time of the Big Bang. Now, simple might not be the word that occurs to you in looking at this event, but remember, you're supposed to look not at the individual particles, but at the flows of energy. And of course, this would be a hopeless and intractable mess if you were just presented with it without some expectation from theory about what you should see and how to interpret it. And by exploiting the properties of QCD, one is able actually to show that this complicated explosion traces back to a fireball, a so-called quark-gluon plasma, of almost freely interacting particles at the high temperatures. The fourth paradigm that I'd like to mention is that symmetry rules. QCD itself was a marvelously symmetric theory. This is very difficult to do justice to without introducing some mathematics, which would take a long time and put you all to sleep probably. But its basic principle, I already mentioned, was symmetry among the different color charges. It's actually a much more powerful thing than that. You can rotate the charges continuously into one another with complex numbers, and you can do it independently at all different points of space and time. It's an enormous structure of symmetry that really dictates the theory in great detail. In this slide, I haven't attempted to do justice to that, but just written down the strong interaction as the horizontal kinds of interactions that change different colors into one another, to complete what's called the standard model, which is our very successful and remarkably complete theory of strong electromagnetic and weak interactions, of the basic interactions that have been observed of elementary particles. We need to include the weak interactions, SU2, and U1 of hypercharge, which is sort of a deformed version of electrodynamics. So the SU2 of the weak interactions works in the vertical direction here, and the U1 doesn't change charges but responds to them with these relative strengths indicated here. And this simple diagram to the educated eye and to the equations that implement the vast symmetry that's implicit here give a remarkably complete and honest description of the interactions of fundamental particles. So it's very successful, but judged by the highest standards and by the fact that it describes so much, we're dissatisfied with this as the final word. It's a beautiful instantiation of symmetry, but it tantalizes us to go further. Because QCD is so much like the theory of the weak interactions and so much like electromagnetism, we'd like to think that there's one underlying structure that underlies them all and contains them all. And they're sort of almost begging for that treatment. So we'd like to do better than having 3 separate interactions and 5 separate classes of particles that don't connect to one another through the interactions. And by expanding our horizons to include 5 colors, or actually this is, for experts, the SO10 unification, you can do much better. You can have all the gluons being related to one another, just one set. They transform 5 different colors into one another, and all the particles observed in the standard model get unified into one structure instead of 5. They're all connected to each other by symmetry, and those funny numbers also get explained. Those funny little subscripts and superscripts I had before. So this is tantalizing. Everything clicks into space. It really looks good. However, there's a fly in the ointment, which is that the strong interaction is called strong for a reason. It really is stronger than the other interactions. So superficially, it looks like the postulate of supersymmetry is of symmetry is a non-starter. However, one of the lessons we've learned from QCD is that the basic charges are within the cloud. We have to strip away the cloud to see the simplicity. We have to go to higher energies. And we can do that with the stroke of a pen, extending those theoretical calculations I showed you before that were verified by experiment to not only QCD, but also the other interactions, and to much higher energies than what's actually been observed. If you do that, you find that, remarkably, it comes close to working using just the kinds of virtual particles we know about, and if you up the ante by including what's called supersymmetry, a very exciting prospect, then it works beautifully, and gravity even fits in roughly. This success of supersymmetry, of symmetry, and its emergence as a new paradigm is a striking feature of 20th century physics, and one that I'm sure you'll be hearing about more in future years. So here are some applications in which QCD either plays a central direct role or plays a helping role in guiding us to how to explore them experimentally. The concept of unification I've talked about. Its experimental consequences are supersymmetry, because we need that to really make the unification work quantitatively, and proton decay, which is a quest. Supersymmetry will double the number of particles and, in some sense, double the space-time dimension of space and time as we know it into new quantum directions, give us a double world if it's seen, and for these calculations to have succeeded, the supersymmetry should be visible at the Large Hadron Collider due to start operating in a couple of years. Supersymmetry also produces an important candidate for the dark matter that astronomers seem to be observing. Improving the symmetry of QCD in a way that's, this should be protection, leads to the existence of a new kind of particle, the axion, which also forms a dark matter candidate and also is a quest for experimental physics. It may appear disturbing that we have two dark matter candidates, but actually I think it's all right, and both may contribute. And then, as a tool in analyzing high-energy experiments, as David mentioned and as I alluded to, 99.9% of what goes on at a modern high-energy accelerators is QCD. We have to understand that very, very well in order to look for the rare events that indicate something new. If we're going to see the fields that implement symmetry breaking in the electroweak interactions, we need and do have accurate QCD calculations to guide the experiments. So I've shown you 4 great paradigms. I'd like to close with perhaps what I think is the greatest lesson, however, coming from asymptotic freedom and QCD and the whole history of the strong interaction, which is really a moral and philosophical one. It's truly awesome to realize that we humans can come to understand nature's deepest secrets, even though they're hidden in utterly alien and remote realms. Our understanding was achieved through a vast international effort involving thousands of people working hard for decades, competing in the small, but cooperating in the large, abiding by rules of openness and honesty. By using these methods, we can accomplish wonders. Thank you.